So this lecture is about ordinary least squares in the case where we have several explanatory variables. So we'll start with a linear regression model and random sampling. So the model looks like this. We have yi, which is determined partly by a linear function of the xi's, and then we have an error term. And the goal is to estimate the parameters beta 1 through beta k. And I think the nicest way to illustrate the process of coming up with estimators of these betas is to do a Monte Carlo simulation, because this is a data generating process for the yi, so it allows us to check if our estimators make sense. So in my simulation study, I have picked k equal to 4. I have 3 explanatory variables from 2 to 4. So this is the setup. I have these 4 beta parameters, and I have a sigma, that's the standard deviation of the error term. Those are the unknown parameters of the linear regression model, at least in the case where we have homoscedastic errors. They will all have a standard deviation of 1. So let me paint this red to remind ourselves that as econometricians, we don't know these numbers. You can just add arbitrary numbers for the x variables, or you can simulate them from any distribution you like, because everything we do in econometrics is conditionally on the observed x's. So here I have just added some simulated data for the x variables. Let's go ahead and put these in green color to remind ourselves that those are observed as econometricians, like that. Next, I will simulate the error terms. The dependent variable, our y variable, will be affected by some random error as well. I will simulate data under the Gauss-Markov assumptions. So I will simulate data such that the variance is constant and such that the explanatory variables are exogenous. I will simulate the errors from the normal distribution. That's not important unless we do inference, that is, unless we do hypothesis testing and confidence intervals, then that will be important. The important part is the 0 for the mean and the constant standard deviation. So let's do that. Let's copy this down, and that we make that red. That's not available to us as econometricians. So now we can simulate our dependent variable, our y variable. That will be green and observed. And according to the linear regression model, it's equal to the intercept, which is in cell B1, do dollar to keep the 1, plus beta 2, B $2, multiplied by x2, which is in cell C2, that's x2, plus beta 3 times x3 plus beta 4 times x4, like that. That's the deterministic part of y. And then finally we add the error term, which is in F2, F$2. So that's the y observation. Let's make a copy of that all the way down. So here's the game that we play in econometrics. Based on just looking at the green data, try to figure out especially these ones, but we will end up also trying to figure out that one, because we will be interested in the variance of our estimators. So one method of estimating these beta parameters is the OLS method, the ordinary least squares. And you should have an understanding of how this works when you have only one explanatory variable. It turns out that the case where you have several is very similar. We begin by defining the same concepts, the fitted values, the residuals, and the RSS. And if you're clever, you can pretty much guess what they look like just based on knowing what they look like for the case with one explanatory variable. So the starting point is now that we want to do this arbitrary for arbitrary constants, these b1 through bk. So think of b1, b2 through bk as our estimates of beta. But we have not yet determined how they should be calculated from the data. So I'm going to add these. So we'll start by just doing guesses for these ones. And 0 is as good as guess as any other thing. So these are my initial guesses for the estimates, so the estimates of beta, which we call b. We paint those guys green, of course, because those are known. Well, they're known in the sense that the way we determine them. Let's add one column in between here. So based on these constants, we can do fitted values. And the fitted values are just the deterministic part of the linear regression model, but where we have substituted the unknown betas with our b's. So let's add the fitted values here. Before we do that, I noticed that I got one too many b's. We only have 4 betas. We should only have 4 b's. So to get the fitted values, I can just borrow this formula. I don't need the error term, the J2. Let's copy that one. Let's paste it in here because it's almost the same. All I have to do is change this 1, which is beta 1, and if I change that to 7, it becomes b1. So let's do that with all of them. 2 to 8, 3 to 9, 4 to 10. Like that. Now all my b's are 0, so my fitted value will of course also be 0, but let's copy that down. But as I change my estimates or my guesses here, the obviously the fitted values will also change. So those are my fitted values for arbitrary b's. We can define the residuals, and they are, just like before, the difference between the actual y and the fitted y. So yi minus y hat. So I have my e here, and it's the y minus y hat. Copy down, make it green. So now I have fitted values, I have residuals, so let's do the RSS, and there is no difference, it's just the sum of squares of the residuals. So let's put that also into our Excel sheet. RSS sum SQ of these ones. That's also known, so we do the green thing. So hopefully you have already figured out how we are going to select these values for b. We are going to select them in such a way that this RSS is as small as possible. That's again the least squares principle. The least squares principle is really unaffected by how many explanatory variables we have because we still have n residuals. So we could play around with this a little bit, maybe increase this to 2. We go from 10,890 to something much, much smaller, 1000. So that was a good one. Maybe change this to 1. Much better. The only difference is that we now have 4 levers to play with trying to minimize RSS as compared to 2 in the linear regression model with just one explanatory variable. So here is the least squares principle. Select B1, B2 all the way to BK such that RSS is minimized. So minimizing RSS by figuring out values for the B's, that's the perfect job for the Excel solver. But before I call the solver, remember that Excel works in the way that anytime I do anything, it draws new random numbers. So let's just freeze these guys, which are random, so that we can get an estimate for this particular data set. We can do that by just copying it. So just do highlight this, copy, and then go to paste and just click this values. So now you can see in the cell, these are just numbers and they are not going to be updated when I click F9. Now clicking F9, nothing happens. So let's do the solver thing. We go to data, solver. We want to minimize RSS, so our objective cell is B12. We want to change the cells B7 through B10 and just make sure you uncheck this one, then solve and keep the solutions. So let's see how we did. 0.78. Well, intercept isn't so good, but typically that's not so easy to estimate. The B2 is much better. It's pretty close to beta 2. This one not so good, but still pretty good, minus 0.7. And this one, well, not too far from 1.1. If you do an experiment like this, you can see that if you change any of these cells, any one, even sort of this one, if you take this to minus 0.7, which is closer to the truth, then you can see that the RSS will actually increase 6.773 to 75 something. So at least using the least squares principle, if I do Control Z, that's the smallest value we can get for RSS. So now these are my OLS estimates. They minimize RSS. And since these guys are now calculated based on the OLS estimates, these are now my OLS fitted values. They're only OLS fitted values if I use the OLS estimates to calculate them. And these guys will be my OLS residuals. This is, of course, such an important problem to find these OLS estimates that you don't have to go through this procedure of defining RSS and minimizing it using the solver. Excel has built-in techniques for handling them, but I wanted to show you with the solver so you get an idea of what's actually happening when we calculate the OLS estimates, that they are based on the idea of minimizing RSS. If I want to get these B's, I can type up something like this. It's going to be in the reverse order. That's the way Excel likes it. B2 and B1. Type up 4 cells, type linest, put your Y's in there, put your X's in there, and they have to be next to each other so you can mark several columns. Put a 1 for the intercept, and I don't want the extra statistics. Shift Control Enter, and you can see that we get the same numbers here as we got from minimizing RSS. If you want a prettier printout from Excel, you can go to Data, Data Analysis, do the regression like this. Okay. Do the input Y, that's this thing. Do the input X, that's this thing. Let's do a new workply sheet. Let's type OLS. Okay. And you get the same results here. You also get some other stuff like standard errors and so on, R squares, and other information that's useful. So it turns out that you can actually solve this minimization problem, that is the minimization of RSS, analytically. In this case, RSS will be a function of 4 variables, b1, b2, b3, and b4. So if you want to solve this problem, you need to differentiate RSS 4 times and set each derivative to 0. And then you need to solve this system of equations. You get 4 equations and 4 unknowns. Unfortunately, this system will be very, very big. So writing down the solution just using the summation sign will be a tremendous task. So when we're faced with this problem of solving systems of equations with many variables, we tend to use matrices instead of writing out the equation one by one. And in matrix notation, the analytic solution turns out to be fairly simple. But we're not going to cover matrix algebra in this course, and it's not terribly important. The only thing you have to realize is that sort of this number, for example, in K13, the B4, it is calculated from a formula, just like the OLS formula in the case when we had one explanatory variable. It's just that the formula is complex and it's just no point writing it down because you would never ever calculate B4 from such a formula. Also, we simply trust that Excel, Gretel, eViews, data, and so on, that they have done their programming correctly and that they actually print out the correct values. So the problem can be solved analytically. We can actually do it, and the solution is still going to call the OLS formula or the OLS estimators. And it's still going to be the case that the only thing we need to calculate these B's is the data on the X variables and the Y variable. But you do need matrix algebra to a matrix notation to express these formulas. And so, as we mentioned, if you use the OLS estimates for B, not just arbitrary numbers for B, then the fitted values are called the OLS fitted values, and the residuals are called the OLS residuals. When we did OLS with just one explanatory variable, we did learn a lot of results that held true for the data when we used the OLS estimates. Well, all of these are still going to be true. For example, one of the results was that the OLS residuals had to sum to 0. That's something we can easily check. If I do equal sum of all the residuals, I will indeed get 0. We had a couple of other results. For example, the average of the y's and the average of y hat was the same. Let's try that. Mean of these guys. And, well, it's not called mean in Excel, it's called average. And if I copy that over here, you have the same average for y hat. Another result from the least squares problem with one explanatory variable was that the sample covariance between the residuals and the x variable was 0. In this case, the sample covariance between the residuals and any x variable will be 0, as we can check. So if I do covariance.s and do the residuals and any of the x variables, you can do this one, you can check yourself with the other ones, you will get 0. So this is 0.00005, 2, and so on. So just because of rounding errors, this is not exactly 0. And you could also check that the sample covariance between y hat data and the x hat data is also 0. In the one variable case, we had the terms TSS, ESS, and RSS, where TSS was the total sum of squares, explained sum of squares, and residual sum of squares. And TSS was the sum of ESS and RSS, and we interpret that as the total variation in the data is the sum of what we can explain with the model and what we cannot explain. That's still going to hold in this case. So let's calculate them. The TSS is n minus 1 times the sample variance in y, so we can just do 14, no, yeah, 14, 15 minus 1 times var dot s of the y data. That's the TSS. ESS is n minus 1 times the sample variance in the fitted data y hat. So 14 times var dot s of these numbers, and RSS was sum of squares of these ones. We can just as well do 14 times the sample variance of that, give us the same thing. And if we check TSS plus, sorry, ESS plus RSS, that is this plus that, we get TSS. So a slight rounding problem. So this holds. R square is defined just like before, no changes. So ESS over TSS, or if you like, 1 minus RSS over TSS. So we can calculate R2. Let's do that here. And it is ESS over TSS. About 99.8% is explained by the model. Pretty much everything else we know about the linear regression model with one explanatory variable carries over. So for example, if I were to increase sigma, making the errors of the residuals larger, that would increase RSS and R square would go down. So finally, we can introduce one new concept that doesn't make sense in the linear regression model with one explanatory variable. And that's something called the adjusted R square, or sometimes called the R bar square. So R square is a measure of fit, the percentage of the total variation that we explain with our model. R square has one, well, at least one problem. And the problem is as follows. If I add more explanatory variables to my model, so I added an x5 and maybe an x6, then you can prove that R square will definitely increase. Well, it could stay at exactly the same value, but it can never go down. Typically, it will always increase. And this will happen actually even if you add explanatory variables that have nothing to do with your data. So if you're trying to explain, for example, the final score on an exam and you add explanatory variables such as the shoe size of the student or any other irrelevant variable, then R square will increase. It's just a mathematical fact. And since we're using R square as a measure of fit, we might actually then incorrectly just claim that the model with these unnecessary and useless variables fit the data better than the model without them. So that's why adjusted R square was invented. The idea is to build in some punishment into the measure of fit for adding more variables. So R bar square will only increase if you add a new explanatory variable and there is a substantial increase in the fit. Its definition is as follows: adjusted R square or R bar square. So these are two common formula for R bar square and they will return exactly the same value, so you can use any one you like. But you can see that if you increase k, everything else is the same. R bar square will actually go down. So if you increase k, this ratio here will go down, this factor here will go down, and 1 minus that factor will go down, so there is a punishment. So what you need then is, when you increase k, you need the increase in R square to be big enough so that the total effect of adding this variable is actually an increase in R bar square. So if you want to compare two models which are identical and they only differ in that one model has more explanatory variables than the other one, that is, model 2 has all the explanatory variables of model 1 plus some more, then you cannot just simply compare the R square values, because model 2 will always have a higher R square value. So people then tend to compare the adjusted R square instead.